Hi class, welcome to How To Video 4. In this video I'm going to show you how to calculate the correlation coefficient, determine the statistical significance of that correlation coefficient, create a scatter plot to showcase the correlation, and then use the scatter plot and the best fit line to predict one score from another. Now the data that we're going to be using in this video are two variables. We're going to be looking at range of motion, hamstring range of motion, and hamstring muscle stiffness. Now to kind of give you an idea of what those are and how we assess those in the laboratory, I've actually got a video here that we'll watch. Let me pull that up. We do this assessment quite a bit in our laboratory here at Texas Tech. This is called a straight leg raise assessment. And as you see here in the picture in the left corner, we have the subject laying down on their back, and then we connect their leg, the leg that we're testing, in this case the right leg, to a machine called a Biodex, which is an isokinetic dynamometer. And what this device does is it can stretch, we can program it to provide a dynamic or passive stretch to the leg that we're testing. And so in the video I'm about to show you, that's what's going on. We're using this isokinetic dynamometer to perform this dynamic stretch. Now from this machine, this isokinetic dynamometer, it provides us with a couple of signals. It provides us with a joint angle signal, and it also provides us with a torque signal. And from these two signals, we can put them together, and that creates an angled torque curve, which is what you'll see over here in the top right corner. From this angled torque curve that's created from this assessment, we can assess things like range of motion and muscle stiffness, the two variables that we're going to be looking at here today. Now finally, for this straight leg raise, what muscle group are we targeting here? What muscle group are we actually stretching? We're stretching the hamstrings. The hamstrings are the muscles in the back of the thigh. And so down below in the bottom, this is an example of a muscle tendon unit of the hamstrings. And watch as we stretch this muscle out further and further and further in the video. Watch how the muscle stretches down here below. And so this is to give you an idea of what's actually occurring, what's happening at the muscle when we perform this dynamic stretch of the hamstrings. And again, this is all in an attempt to assess range of motion and muscle stiffness, those two variables we're looking at today. So let me show you the video. Watch. Okay, you can see here the leg is slowly raised up by the Biodex. As the leg is stretched further and further, that muscle tendon unit is being stretched. And then simultaneously over here, this angled torque curve is being produced. As soon as the subject reaches their max range of motion, we program the device to bring the leg back down to baseline. Okay, that was it. Okay, so a fairly simple test, all right, to assess those things. It only takes a few seconds like you saw in the video. And then, like I said, from this test, we get an angled torque curve. Okay, that Biodex, that isokinetic dynamometer, gives us an angled torque curve. And from this angled torque curve, okay, something like this here, all right, this is a typical angled torque curve produced from an assessment that we just watched. We can measure those two variables that we're going to be looking at today. Range of motion of the hamstrings, and then also to hamstring muscle stiffness. The range of motion, how do we measure it from the angled torque curve? The range of motion is pretty easy. It's just a single measurement. It's actually the final measurement in the angled torque curve. So range of motion, which is essentially the max range of motion, the maximum amount of flexibility a person has, that's measured at this point on the angled torque curve where my mouse is. So to figure out what the max range of motion in this example is, in this angled torque curve, all we would do is take this final point here, and we would go down to the x-axis, the horizontal axis here. And yeah, just looking at the graph here, that max range of motion for this participant would be about 110 degrees. Okay, the range of motion would be about 110 degrees. To measure muscle stiffness, it's a little bit more difficult to measure. We have to measure the slope of this angled torque curve. That's how we measure muscle stiffness. It's the slope of this curve. Now we can measure muscle stiffness at any part of the curve. I just so happen to show it here. Okay, to measure the slope of a line, you've probably heard this maybe in algebra class, rise over run. Basically, we're doing the same thing. We're just changing the variables. The rise, okay, part is the change in torque. And the run part is the change in range of motion. Okay, so rise over run, torque divided by range of motion. That's how we measure muscle stiffness. Range of motion is measured in degrees. Muscle stiffness is measured in Newton meters per degree. Remember, muscle stiffness is the slope of this curve. It's the change in passive torque divided by the change in range of motion. Passive torque is measured in Newton meters. Range of motion or joint angle is measured in degrees. And so when we put those two together, yeah, it's Newton meters per degree. So it does make sense that these are the units for muscle stiffness. Like I said, muscle stiffness is a lot more difficult to measure, okay, as opposed to range of motion. And so what we're going to be doing today in today's video is looking at the correlation, looking at the relationship between these two variables. Because range of motion is a lot easier to measure, we want to look at the correlation in order to, and we talk about this in PowerPoint 7, and I encourage you to look at and study and review carefully PowerPoint 7. It talks about this. We can predict one variable from another using correlation. Okay, that's one of the benefits of looking at the correlation coefficient, examining relationships, is we can predict things. We can predict one variable from another. Because muscle stiffness is a lot more difficult to measure compared to range of motion, we could simply measure range of motion and then use that value to predict muscle stiffness of a patient, of a person. And so, yeah, so this does have a lot of practical significance, what we're trying to do here today and what we talked about in the PowerPoint for this week, PowerPoint 7. And so as we go through this video, yeah, keep that in mind, the implications, the importance of what we're doing. Again, with correlation, one of the primary things that we can obtain, that we can gain from doing this statistical procedure is we can predict, is we can use correlation to predict things. And so just keep that in mind as we go through the practice assignment in the how-to video today. Now, what I've got pulled up, similar to our previous how-to videos, is our Word document assignment on the right side, and then an Excel sheet on the left side. I've got these two pulled up so we can look at them together simultaneously. Like I said, we're going to be looking at hamstring range of motion and muscle stiffness. Now that you've seen that video, you have an idea of what those things are, how we assess them in the laboratory. Take a look at the sample that we're going to be looking at here today in this how-to video, professional dancers. Now, in your assignment number 4, you're going to be doing the same thing. You're going to be examining the relationship between hamstring range of motion and muscle stiffness, but it's going to be in a group of female gymnasts. Now, if you think about both of those sports, professional dancing, gymnastics, both of those sports, they require range of motion. They require flexibility in order to be successful in that sport. A lot of times, especially with gymnasts, dancing too, those that are most flexible, those that have the greatest range of motion, those are the ones that are most successful in that sport. And so these variables that we're looking at today, range of motion and also too muscle stiffness, they're very, very important, okay, not only for the general population as a whole, but also particularly important for these types of athletes, okay, these gymnasts, professional dancers. Now, before we go on, again, a little bit more background on this. The theory behind muscle stiffness is that the lower the muscle stiffness, the less risk someone has at having an injury. Okay, and again, when we talk about the hamstrings, what's a very common injury? A hamstring pull or a hamstring tear. And so those with lower stiffness values, they are at a lower risk of having a hamstring tear, a hamstring pull, one of those injuries. Those with higher muscle stiffness, they are at a greater risk of having a hamstring pull or hamstring tear. So yeah, so not only is range of motion important for performance for these athletes, muscle stiffness is also important too for these athletes from an injury standpoint. So yeah, both of these variables that we're looking at are very, very important for the health and performance of these populations, of these athletes. Again, like I said, in this video, the data that I'm going to be working with is in professional dancers. In your assignment 4, you're going to be working with female gymnasts. Okay, again, keep that in mind. Just like in the previous videos, your data is going to be different than the data that I'm going to be working with here today. And so my answers, okay, to the questions for this assignment that I'm going to show you today are going to be different, okay, than the answers, are most likely different. They could be the same, okay, but yeah, most likely your answers are going to be different than my answers here today. So again, just keep that in mind. Again, this video is designed to give you an example of how to work the problems, okay, identical problems that you'll see in your assignment 4. Again, the only difference is you're going to be working with different data than me. Okay, let's continue here. It says here at the top, a researcher wants to examine the relationship between these two variables in a group of 17 professional dancers. Below are the results. Okay, here are those results there. Copy and paste these data into an Excel spreadsheet. Use these data to answer the following questions. Okay, so the first thing it says is we need to copy and paste these data into an Excel spreadsheet. And also too, before I start, and before I forget, and again, remember you need to do this too, don't forget to type in your name at the top left corner of the page. Okay, let's copy and paste these data into an Excel spreadsheet. All you have to do is highlight the data just like I've done, right click, copy, and then go over here to your Excel sheet, and then you can paste them into the Excel sheet. And yeah, I'm going to do that there. Okay, so now that we have our data and we've pasted it into our Excel sheet, now we're ready to go and answer the questions. Let's scroll down to question number 1. Question 1 says, what are the means and standard deviations for range of motion muscle stiffness? Report them as mean plus or minus standard deviation. Okay, remember we talked about mean and standard deviation in previous how-to videos and how to calculate those. Mean is a measure of central tendency. Standard deviation is a measure of variability. Yes, oftentimes in research, these are one of the primary statistics, okay, that readers want to see. They want to see what the mean is, they want to see what the standard deviation is, and so it's really important that we know how to calculate these and that we can report them. And so, just like we did before in a previous how-to video, I'm going to record down all of the statistics, all that we calculate down below the data. And so I'm going to type in here mean, and then down below I'm going to type in standard deviation. SD symbolizes standard deviation, and then I'm going to calculate the mean and standard deviation for both range of motion and muscle stiffness, okay, just like the question asked. And so, and I'm going to bold these two so it's easy to see. So in order to calculate the mean, and again, remember I've shown this in previous videos. I'm not going to spend a lot of time on this. I'm going to go through it pretty quickly here. And so if you need further guidance on this, please refer back to our previous how-to videos. In order to calculate the mean, I'm going to highlight the empty cell next to the mean. I'm going to go to function. Remember, the mean is the average. I'm going to click on average, okay, or search for it, and then click average. Click OK. And then I'm going to highlight all of the values, all the data points, right? Each subject here has a data point for a range of motion. I'm going to highlight all of those. And then once I do, I'm going to click OK. Okay, now I've got my mean value there. I'm going to do the same thing for standard deviation. I'm going to go up to function. I'm going to go to standard deviation. I'm going to highlight all the values, and then I'm going to click OK. Okay, and then yeah, the standard deviation is going to appear in that cell that I had originally highlighted. All right, so now that I have the mean here for range of motion, I have the standard deviation. Take a look at the instructions over here. It does say round to the second decimal place. So let's go ahead and do that. So to do that, all we have to do is highlight our two calculations that we just made, the mean and standard deviation for range of motion. if we go up here to the top and we go to this value, decrease decimal, click on it, notice how the decimal places are decreasing now in the cells that I have highlighted. And I'm going to go all the way to the second decimal place. Notice, what does that mean, rounded the second decimal place? Well, if you take a look here, here's the decimal. Second decimal place is 2 decimals to the right of that decimal. So 1, 2. Notice how I have 2 numbers here right to the right. And so yeah, that's what that is. We round it to the second decimal place. That just means we have 2 numbers here to the right of the decimal. Okay, again, it also says we need to calculate the mean and standard deviation for muscle stiffness, okay, or passive stiffness, as it's shown here. In order to do that, it's very easy. In order to calculate the mean and standard deviation for muscle stiffness, all we have to do, similar to what we did for range of motion, is highlight the empty cell here under stiffness. Go up to function, go up to average, click OK, highlight all the data points for muscle stiffness, and then click OK. Same thing, standard deviation, highlight the empty cell, go to function, go to standard deviation, click OK, highlight the values for stiffness, and then click OK. Again, we need to round these to the second decimal place. So click and highlight both, go up to our decreased decimal, and then decrease until we get to 2 decimal spots. Okay. I'm also going to make a quick correction here. I should have put here, and I did this for your assignment, but I didn't do it for my assignment here. Passive stiffness, muscle stiffness, we can use those two terms interchangeably. They mean the same thing. And so I'm going to change both of these. Again, just to avoid any confusion here that you might have. You might be thinking, well, wait, I thought we're measuring muscle stiffness. We are, okay? Just know that, yeah, they actually mean the same thing, okay? Passive stiffness, muscle stiffness, we can use those two terms interchangeably. And so, yeah, so just FYI, just to avoid any confusion, I'm going to change that real fast. And again, it shows on your assignment. I just forgot to change it on mine. Okay, so now that we've calculated the mean and standard deviation for both range of motion and stiffness, we rounded them to the second decimal place. Now we're ready to input those values into our Word document, into our assignment. So for range of motion, the mean we just got through calculating here is 128.41. Notice in the instructions it says we want to report the mean and standard deviation as mean plus or minus standard deviation. So let's do that. In order to get this plus or minus symbol, you can find it up here if you go to Insert and if you go to Symbol, or you can simply, what I'm doing here, I'll show you, you can simply highlight this, right click, copy, and then you can paste it right here. That's the easy way. Okay, plus or minus, and then you can write in the standard deviation. Again, I want you to write it or report it as this because a lot of times in research, this is the way it's reported. It's reported as mean plus or minus standard deviation. And so I want you to get in the habit of reporting it like this. The standard deviation we just reported, 18.56. Okay, and again, we'll bold all of this, okay, to indicate our answer here. Remember, range of motion, it's measured in degrees. And so, and I'm going to cheat here too. I'm going to go ahead and pull this from our table. But yeah, it's always good to get in a habit of including the units, all right, when you report mean plus or minus standard deviation. So you can include the units right after, okay, right after the mean plus or minus standard deviation. So I'm going to include degrees right here, right after, right at the end of the standard deviation, okay, to help indicate my units. Let's do the same thing for muscle stiffness. Let's report the mean plus or minus standard deviation. The mean is 1.51. Okay, I'm going to take this and copy and then paste it down here. Plus or minus standard deviation is 0.18. And remember, the units for muscle stiffness are right up here, Newton meters per degree. And so again, I'm going to cheat. I'm just going to copy this and then I'm going to paste it down here. Okay, Newton meters per degree. All right, cool. So now we've got our mean plus or minus standard deviation for both variables range of motion and muscle stiffness. Let's go to the next question. What would the null hypothesis be for the correlation coefficient between range of motion and muscle stiffness? To answer this question, please refer to PowerPoint 7. In the PowerPoint, there's a slide that talks about, well, there's several slides that talk about statistical significance. And on one of those slides, it talks about the null and alternate hypotheses when we work with correlations. For the null hypothesis for a correlation coefficient, what is it going to be? Yeah, if you look at the PowerPoint, it states this. Basically, it states, the null hypothesis states that R, okay, the correlation coefficient, and yeah, if you take a look at the PowerPoint, it'll talk about this, but this lowercase r that's italicized, this is the symbol that we use to represent the correlation coefficient, the Pearson correlation coefficient, so just keep that in mind. But basically, the null hypothesis states that R is not statistically significant. Now, if we want to get a little bit more specific, okay, especially given the question that was asked, again, the question is specific. It's between the variables that we're looking at, between range of motion, muscle stiffness. You could expand upon this, okay? So yeah, the null hypothesis in its simplest term is R is not statistically significant. You could say the correlation coefficient, R, and I'll italicize that. Again, with this lowercase r, the symbol, it needs to be italicized. That's the symbol that represents the correlation coefficient. The correlation coefficient between range of motion and muscle stiffness is not statistically significant. Okay, so again, basically what I've done is just expanded upon what the PowerPoint stated. Yeah, in its most simplest terms, the null hypothesis when dealing with correlations, what is it? Yeah, basically it's R is not statistically significant. All I've done here is just expanded upon that. I'm basically saying the same thing. I'm just being more specific to the research question. The research question asks about the variables we're looking at, the correlation coefficient between range of motion and muscle stiffness. So to be more specific to answer that question, I could say something like this. The correlation coefficient between range of motion and muscle stiffness is not statistically significant. Okay, basically the same thing that's stated in the PowerPoint, but just more specific to our research question. And again, you can, for your assignment number 4, you can answer it just like I've answered it here for question number 2. You can state the exact same thing that I've done here. The correlation coefficient between the two variables, range of motion and muscle stiffness, is not statistically significant. You can actually use this same sentence here, okay, for the null hypothesis. That's what the null hypothesis is. It's stating that the relationship, the correlation coefficient between these two variables is not statistically significant. Okay, let's move on to the next question. Question 3, it says, suppose the researcher sets the alpha level at 0.05. Calculate the Pearson correlation coefficient between range of motion and muscle stiffness. Okay, so let's go ahead and do that one first. That's the first one that's here left blank for us. R, okay, remember the correlation coefficient is symbolized by the lowercase italicized letter R. And so yeah, so this is where we're going to put our answer here for that question. Calculate the Pearson correlation coefficient. In order to calculate it, it's pretty easy. I'm going to go back over here to my Excel sheet. I'm going to include that statistic here, R. Okay, I'm going to italicize it. I'm also going to bold it here so it's easy to see. I'm going to put that here in that left column underneath my other statistics that I already calculated, mean and standard deviation. And then I'm going to calculate the R in this blank space here. Again, remember R is the correlation between these two variables. So to calculate the Pearson R, all you have to do is highlight the empty cell here next to our label, okay, next to R, what we're trying to calculate. Go to function. Go to Pearson. Okay, I have it here, all right, in my functions here. But if you don't have it on yours, you can search for it. Just type in Pearson, hit go, and then yeah, it should be your top selection here, Pearson. And take a look, yeah, it returns the Pearson product moment correlation coefficient. It solves for this statistic here, R, which is what we're looking for, right? Okay, that's what we're trying to solve. So click OK. That's the function we want to use, the Pearson R correlation coefficient. Array just means a set of data. And so array 1 is going to be for our first variable 1, our first set of data, which in this case is range of motion. So I'm going to click and highlight all of the data points in that array. Okay, now that I've done that, I'm going to click on array 2. Array 2 is for variable 2. In this case, variable 2 is muscle stiffness. In order to calculate the array or determine the array for muscle stiffness, again, just click and hold and highlight all the data points for muscle stiffness. Now that we've done that, we're ready to go. Click OK. And then that calculates the Pearson R correlation coefficient in our cell that we selected. It says in the instructions we're going to round to the first 3 decimal places. So to do that, all you have to do again is go up here, go to decrease decimal. Okay, once the cell is highlighted, decrease decimal, and you can decrease it to 3 decimal spots. 3 decimal spots, what does that mean? Okay, just 3 values to the right. So notice the decimal place here, 1, 2, 3. We've got 3 numbers, 3 values to the right of that decimal. That's what it means when it asks you to round to the first 3 decimal places. We round to the first 3 decimal places here. It talks a little bit about this in the PowerPoint. We rounded to the first 3 decimal places oftentimes in research for greater precision. I know in the PowerPoint, oftentimes, and I did this for kind of simplicity, oftentimes in the PowerPoint I would round R to the nearest 2 decimal places. Okay, but yeah, to be more precise in our calculation of R, oftentimes in research studies we do round it to the first 3 decimal places. And so again, I'd like for you to get into a habit of doing that, and so that's why we're going to do it here in this assignment. Okay, so now that we've calculated the Pearson R correlation coefficient, negative 0.702, let's go ahead and record that down in our assignment. So negative 0.702, that's our Pearson R correlation coefficient. Now let's go to the second question. The second question says determine the p-value. Okay, determine the p-value for this corresponding correlation coefficient. We also want to round it to the first 3 decimal places. In order to determine the statistical significance of R, again, it talks about this quite a bit in the PowerPoint. So again, I encourage you to please review, please study the PowerPoint. It talks about this. We're going to use a website on the internet in order to determine the p-value, okay, in order to determine the statistical significance of R. The website is listed in the PowerPoint, and so please, again, go to the PowerPoint to find the website. I'm going to go ahead and pull it up here on my screen. Here it is. All we have to do is just input the R score that we just got through calculating. And let me make this a little bit smaller so you can see this simultaneously with our assignment. The R score, okay, and again, I know it's a capital R here, right? And I know we talked about Pearson R, it's a lowercase r, italicized. Basically on this website, again, it means the same thing, okay? It's looking for that lowercase r score, and that's where we're going to input it. So the Pearson R value that we just got through calculating in Excel, that's what we're going to put here for the R, okay? That's what we're going to put here for the R score, the R value. So I'm going to type it in, negative 0.702. For N, what is N? Okay, now I know again N, it's capitalized here in our previous PowerPoints, and I believe in PowerPoint 7 it also shows this too. N, especially when we're dealing with samples, random samples, we abbreviate it as a lowercase n, but here on the website, just know it means the same thing. This uppercase N, it means the same thing as the lowercase italicized n. It's the sample size. And so if you go back up to the very top, what's our sample size in this problem? Well, our sample size is the number of subjects, okay, that we're testing. And in this particular assignment that I'm working in this how-to video, we have 17 subjects. So 17, that's our sample size. That's what N is equal to, 17. Okay, and again, notice that for each subject we have a pair of values, right? A pair of scores. One range of motion score and one muscle stiffness score for each subject. And so it talks about this in PowerPoint, in PowerPoint 7. So again, I encourage you to read and study that carefully. Yeah, for each subject we have a pair of values. So how many pairs of values do we have? Yeah, we have 17. We have 17 subjects, so we have 17 pairs of values. So that's what we're going to put in here for n in this example here. And again, remember, it may be different, right? It may be different, okay, for your data. Likely it's going to be. Your R value is going to be different than mine. Your sample size may be different than mine. Okay, so again, just keep that in mind. But again, for my sample size that I'm showing in this video, it's 17. The significance level, what is that? The significance level, you can think of that as the alpha level. Okay, we can use those two terms interchangeably. They mean the same thing. Alpha level, significance level, it means the same thing. The alpha level is the level or is the value that we set to determine statistical significance. So yeah, it makes sense that they mean the same thing, the alpha level, the significance level. So because the researcher sets the alpha level at 0.05, that's what the significance level is. The significance level is also going to be 0.05. It's the same thing. It's the same thing as the alpha level. So we need to make sure that that's selected, okay? And I believe that's the default here in this website is 0.05. So yeah, so we make sure that that's selected, 0.05. We've inputted our Pearson R value. We've inputted our sample size. Now we're ready to calculate the p-value. Hit calculate. And then that calculates the p-value for us, which is listed down here below now. Okay, so this is our p-value here that we're going to input into our assignment. This is how we calculate the p-value, okay, for the R value. And again, if you need more information on the p-value, I encourage you, again, take a look at the PowerPoint 7. Also take a look at our previous PowerPoint, PowerPoint 6. PowerPoint 6 also goes into great detail about the p-value, okay, p-value being, okay, the probability, okay, representing probability. So the p-value in this case, what we just got through calculating using the website, is going to be 0.00. Again, remember, we're going to round to the first three decimal places. So 001, okay, look at the next one is a 6. So what are we going to do with this third decimal spot here? We're going to round it up. Okay, because this is greater than 5, we're going to round this up to 2. So for my p-value here, it's going to be 0.002. Okay, rounded to the first three decimal spots. Okay, so now we've calculated the R value. Now we calculated the p-value. Okay, our last question says, based on this p-value, should the null hypothesis be accepted or rejected? Again, take a look at the PowerPoint 7. It goes into this in detail. But because the p-value here that we just got through calculating, because it's less than, 0.002 is less than the alpha level, 0.05, because it's less than, what are we going to do? We're going to reject, okay, the null hypothesis. And so you can just simply type in here, okay, your answer, reject. Okay, and again, your answer might be different. It might be accept, okay, for your data. So again, keep that in mind. It could be the same. It could be reject. All right, again, remember, you're dealing with different data, okay? And so just keep that in mind. It could be the same answer. It could be reject, but it could be accept too. So just remember that. But yeah, when the p-value is less than the alpha level, we reject the null hypothesis. Okay, let's go on to the next question. The R value calculated in question 3, okay, up here, we just got through calculating R value in question 3, indicates A, all right, and then we have a multiple choice question here. Okay, what type of correlation does the R value indicate? In order to answer this question, we can get this from PowerPoint 7. I'm going to go ahead and pull that up. Okay, let me get that up here. All right, here it is. Here's our PowerPoint 7. This particular slide right here in PowerPoint 7, this is where it talks about the magnitude, the size of the correlation coefficient, and how we determine that. And these come from guidelines from a previous research study. And so yeah, so from this research study, they provided guidelines for us in order for us to help interpret the size of the correlation coefficient. And so if you take a look at the correlation coefficient that we just got through calculating in this how-to video, negative 0.702, where does this fall under? Well, to start off here, we need to make a decision. Is it a positive or is it a negative relationship? How do we know? Well, we know by the sign here in front of R. If it's a negative value, it's going to be a negative relationship. So that's going to draw our attention down here. Okay, so yeah, so immediately right off the bat, you can ask yourself that question. Okay, are we dealing with a positive correlation? Okay, is it positive 0.702 or is it negative 0.702? Okay, or whatever the R value is. In this case, it's a negative, so we're going to go here to negative relationships and then look down below. Now, negative 0.702, where does that fall under? It's going to fall under right here, right? R equals negative 0.70 to negative 0.99. It's going to fall within this range, right? That negative 0.702, it's going to fall within this range here. So what would my answer be? Well, if you take a look, a correlation, an R value that falls within this range is considered a strong correlation. It indicates a strong correlation. And so yeah, to answer this question, the R value calculated in question 3 indicates A. Yeah, I'm going to select this one, C. That's going to be my answer here. Okay, so I'm going to bold it and then I'm going to highlight in yellow in order to indicate, in order to show. Okay, again, when I grade this, I want to be able to see what you select. So make sure and do that. Make sure and bold and highlight your answer so I can see which answer choice you selected. Again, remember, your data is different than mine, so your answer may be different, okay? It may not necessarily, it could be, it may be a strong correlation, okay, but it could be something different. So again, just keep that in mind, okay? My R value that I calculated here is indicative of a strong correlation. Okay, let's move on to question 5. Is the R value statistically significant? In order to answer this question, all we have to do is go back up to question number 3. Because of our statistical decision here, because we reject the null hypothesis, and again, remember, we reject the null hypothesis because the p-value is less than the alpha level that we set it to. It's less than 0.05. Because the p-value is less than the alpha level at 0.05, we reject the null hypothesis. What does this mean? Yeah, this means that when we're dealing with correlations and we get a p-value less than 0.05, this means that our R value is statistically significant. Again, we can conclude that. By rejecting the null hypothesis, we can conclude that the R value, yes, is statistically significant. So that's going to be my answer. Yeah, here for the multiple choice is yes. Yes, because the null hypothesis up here, because we rejected it, by rejecting the null hypothesis, we are concluding that the R value that we calculated is, in fact, statistically significant. Now, if our p-value was greater than 0.05, right, we would accept the null hypothesis. And if we accepted the null hypothesis, by accepting it, is the R value statistically significant? No. Okay, by accepting the null hypothesis, we're saying that the R value is not statistically significant. And so we would answer no, okay, if that was the case. And again, that might be the case for you in your data. So again, just keep that in mind as you're working through answering these questions. Question 6, is range of motion significantly related to muscle stiffness? Again, it's based upon our answers above. Because we rejected the null hypothesis, by rejecting it, yes, that's what we're basically stating. By rejecting the null hypothesis here, because our p-value is less than 0.05, because it's less than our alpha level, we are saying that yes, the R value is statistically significant, and we are also saying that range of motion, okay, is significantly related to muscle stiffness, or vice versa. Muscle stiffness is significantly related to range of motion. Okay, they are related to each other. And so yeah, so they are significantly related. We can say that, okay, based upon our answers here. Because the p-value is less than 0.05, yes, range of motion is significantly related to muscle stiffness. So I'm going to select that as my answer choice. Again, if it wasn't, okay, let's say the p-value was greater than 0.05, we would accept the null hypothesis and we would say, we would conclude that range of motion is not significantly related to muscle stiffness. So our answer would be no here. Okay, so again, it depends upon our answers up above. Okay, it depends upon our p-value. If our p-value is less than 0.05, then yeah, our R value is statistically significant. Okay, the one variable is significantly related to the other. If it's greater than 0.05, then no, the R value is not statistically significant. It's not related, okay? One variable is not related, significantly related to another. Okay, so again, hopefully you can see that. It's all dependent upon our calculations up above, particularly the p-value, okay, that we determine. Okay, moving on, question 7, calculate the coefficient of determination. All right, so in order to calculate that, I'm going to go back to Excel, and I'm going to put that here. I'm going to put R, I'm going to copy it down here, and then I'm also going to put next to R, okay, a 2. And then in order to superscript that, you can just highlight, and then you can go up to Font, and then you can go up to Superscript, select it, and click OK. And then, yeah, notice how it superscripts it. You can italicize it if you want. Okay, and so, yeah, so that's how you superscript a number in Excel. And notice, again, that's what we're calculating. The coefficient of determination, it's symbolized by this lowercase r italicized and then squared. And so in order to write that in Excel, okay, just like I've done, okay, you do those procedures that I just got through showing you. Basically, r squared is just like what it says. We are squaring the r value. So the r value that we calculated up here, this negative 0.702, all we have to do to figure out the coefficient of determination is just square it. Okay, that's all it is. It's simple. It's easy. The coefficient of determination is very easy to calculate. Once we've determined the Pearson R value, we can easily calculate the coefficient of determination. So let's do that in Excel. In order to do that, all you have to do is click on the cell here next to our label, okay, for the variable we're looking for, the coefficient of determination. Hit equals on your keyboard. Click on your R value that you calculated up here above. Again, in this case, it was negative 0.702. And then on your keyboard, hit Shift, and then hit the number, and hit Shift and hold Shift, and then click on the number 6. So Shift, hold, and then click on 6. What that will provide is a caret. Okay, so by holding Shift and then clicking 6, that provides what we call a caret, which basically means exponent. Okay. And then we can type in the exponent. We're going to square it. Okay, so we're going to type in a 2 here. Okay, squared. We're going to type in a 2. And so again, that's what we're doing, right? To calculate r squared, all we have to do is square this value. So to do that in Excel, okay, we take our r value, which is in this cell, B23, and we square it, okay, by putting this caret here and then putting a 2. Once we've inputted this equation into our cell, click Enter. And then that should provide us with the coefficient of determination. It says here we need to round the coefficient of determination to the second decimal place, so let's do that. Again, just decrease the decimal spots until we get to 2. Right there, okay, 1, 2, okay, to the right of the decimal. There we go. So our coefficient of determination, what is it? It's 0.49. Now you might be thinking, how did you get a positive? How did you get a positive value when the r value is negative? Well, if you think about it, simple math, simple algebra 101, what are we doing when we square a value? We're multiplying by itself. Basically, we're taking negative 0.702 and multiplying by negative 0.702. When we multiply a negative times a negative, we get a positive, okay? Basic algebra 101, and so that's why. That's why the coefficient of determination, and keep this in mind, here's a good rule of thumb. The coefficient of determination is always going to be a positive value. Okay, it's always going to be a positive value. So again, why? Because yeah, regardless of whether the Pearson R is a negative or a positive, when we multiply a negative value by itself, when we multiply a positive value by itself, okay, again, that's what we do when we square a value. We should get a positive value, a positive answer. So yeah, our R squared value is a positive 0.49. I'm going to record that down here in my assignment, 0.49. And again, it could be different for your data, right? So again, just keep that in mind. Explain variance. That's the next question. It says, based on your calculation of the coefficient of determination, how much of the variance as a percentage in range of motion can be explained by the variance in muscle stiffness? Okay, so we're going to calculate the explain variance. That's really easy to do. And again, it talks about all of this, coefficient determination, explain, unexplained variance. It talks about these things in the PowerPoint. So again, I know I keep saying that, but please study, review the PowerPoint, PowerPoint 7. It goes into great detail in all of these things that we're doing here today. I'm going to type in explain variance. Okay, again, other variables here, statistics that we're calculating. Unexplained variance. Okay, I'm going to bold these two. I'm also going to increase the size of my cell so it fits all within the cell here. Okay, so yeah, you can do that as well if you'd like. To calculate the explained variance is directly associated with the coefficient of determination. And so because of that, all you have to do here to calculate the explained variance is go to, okay, after you type in your labels here for the statistics, go to the empty cell next to the label, click on equals on your keyboard, and then all you have to do is click on the cell here above where you calculated your coefficient of determination, and then simply just click enter. Okay, now I know you're thinking, well, wait, it asks for you to calculate as a percentage. Yes, I know that, and we'll come back to that in just a second. Okay, but yeah, as of right now, just do what I did there. Okay, the explained variance is directly related to the coefficient of determination. The unexplained variance, what is that? Okay, and you'll notice that's the next thing that's asked in question number 7. How much of the variance is left unexplained? To calculate this, it does, again, briefly talk about this in the PowerPoint. The equation for unexplained variance is simply this here. If you want to calculate unexplained variance, which we do for question 7, highlight the cell here next to the label, click equals on your keyboard, and then hit on your keyboard 1, okay, the numeral 1, minus, and then we're going to subtract the explained variance. So the unexplained variance is just the opposite of the explained variance. So to calculate it, all we have to do is go 1 minus the explained variance. Okay, or 1 minus the coefficient of determination, 1 minus 0.49. Okay, and that gives us a 0.51. Now again, like I said, I know it says here we need to calculate them as percentages, okay, these variances. To do that, it's really easy. All you have to do is highlight these two here, our explained and unexplained variance. Go up to the top, and then go under, again, it's under this Home tab, go to percentage here, click percent, and then voila, it changes it to a percentage. And again, you know this from Algebra 101, I'm sure you've gone over it before. In order to get a decimal to a percentage, all you have to do is just multiply it by 100. So you could do that too if you wanted to. Just multiply this value by 100, okay? So 0.49 times 100 is 49%. So yeah, so now we've calculated the explained and unexplained variance, okay? How much of the variance in range of motion can be explained by the variance in muscle stiffness? 49%. How much of the variance is left unexplained? Yeah, that's the remaining 51%. So what does this mean? Basically, this is just stating that muscle stiffness can explain a large portion of the variance in range of motion, 49%. But there's also a large portion of the variance that's left unexplained. What does that mean? That just means that other variables are influencing range of motion. Okay, other variables other than muscle stiffness are influencing range of motion, and they account for this other variance. Okay, other variables that we didn't measure here in this example, this research study. And so yeah, so another variable that influences, for example, another variable that influences range of motion, just FYI, is someone's ability to tolerate pain. Yeah, if you can tolerate more pain, then you can stretch further. You have a greater range of motion. And so that's another key variable that's likely unrelated to stiffness that influences or explains some of the variance in range of motion. And so that could be, okay, that's just one example. That could be a variable, a factor that explains some of that unexplained variance in range of motion that wasn't explained by muscle stiffness. And so that's what that means. Okay, so with the coefficient of determination, we can determine this. We can determine the explained and unexplained variance. How much of the variance is explained by the variable that we're looking at, and how much is left unexplained. Okay, so let's input those values, our answers, into our assignment. So explained variance is 49%, and unexplained variance in this problem, in this example here, is 51%. And again, remember, your data is different, and so your answers may be different here for question 7. So again, just keep that in mind. Okay, let's continue. All right, so question number 8, it says we're going to create a scatter plot. And remember, a scatter plot from PowerPoint 7, it talks about this. That's a visual description of the correlation coefficient. That's how we visually show the correlation between two variables, is by creating a scatter plot. So that's what we're going to do here. We're going to create a scatter plot to showcase this correlation between range of motion and muscle stiffness. In order to do that, it's fairly simple. Just click on an empty cell like I've done here, okay, up here in column E. And then what you do next is you're going to highlight the data. Okay, so highlight the data. You don't have to highlight the labels, just highlight the data points for both variables. Okay, all the data points for range of motion and stiffness. Go to Insert, go to Chart, go down here to Scatter, Insert Scatter, and then it's going to be this first answer choice, Scatter. Okay, that's the one that you're going to select, and then yeah, voila, we've created a scatter plot. Now, just like before in previous assignments, there's quite a few instructions here on what I want you to do. Again, remember, this is how I grade you on this assignment. So not only are you getting the correct answers, okay, obviously I grade you on that for this on the assignments. I also grade you on how well you can follow instructions, okay, especially instructions like this here for question number 8, when I have you create a graph. And so it says here, create a scatter plot of the relationship between range of motion on the horizontal axis. Yeah, if you do it just like I've done here, then yeah, the range of motion should automatically be on the horizontal axis. In order to check to make sure, you can just take a look at the values. Again, take a look at the values here for range of motion compared to stiffness. Range of motion, these values are quite a bit larger, right? They're all in like the hundreds. Take a look at stiffness. They're very, very small. They're all within like 1 to 2, okay? 1.44, 1.85. They're very small in comparison to range of motion. And so yeah, it makes sense here. Look at our scale. Look at these large values here. This is range of motion. And then look at these small values here. This is reflecting stiffness. And so yeah, that's an easy way to determine, okay, which variable is which. Yeah, if you're having trouble. In this particular example here, range of motion is a lot larger than stiffness, and so yeah, we know, okay, based on the graph that was created by default, that this down here in the horizontal axis, on the x-axis, this is range of motion. These smaller values here, that's reflective of muscle stiffness. Okay, it says include labels for both the horizontal and vertical axes. All right, so yeah, so we've got our range of motion on our horizontal axis. Let's include a label for this. In order to do that, yeah, very similar to what we've done in previous how-to videos. All you have to do is highlight the graph like I've done here where the border is around it. Go to Add Chart Element, go to Axis Title, go to Primary Horizontal, and then that's where we're going to type in our axis title. It says it specifically in the instructions. We're going to title it Range of Motion, and then in parentheses we're going to put the units. Okay, the units are in degrees. Again, we can just cheat here if we want. Let's see if it'll do it for me. And then yeah, so you can just copy, okay, the degree sign, or you can go to Insert and then go to Symbol, and you can find the degree sign under the symbols. That's another way of doing it. Okay, but yeah, simply you can just copy and paste and then close parentheses there. Range of motion, remember, is measured in degrees. Let's go ahead, just like it shows here in the instructions, let's go ahead and bold it. Okay, bold it. We can also make sure that it's in black font. Okay, black, bold. All right, make it very visible, very easy to see. Let's do the same thing. Let's create a vertical axis now, a vertical axis title. Again, highlight the graph, go to Chart Design, go to Add Chart Element, go to Axis Title, go to Vertical. That creates a vertical title. This title needs to be labeled muscle stiffness, right? This is where our, yeah, muscle stiffness. Newton meters. Yeah, the units are Newton meters per. You can just put a slash there, per, and then yeah, degrees. Again, you can just copy this, right? And then you can put it down here, degrees, and then hit paste, and then you can copy it right there, and then hit close parentheses there. All right, so yeah, so now we've got our muscle stiffness, okay, labeled here on the y-axis, good. And again, we can change it to black font, we can bold it just to make it a little bit more visible, easier to C. It says remove, next instructions, remove the title. All right, so remove this, so you can just click on it and then hit delete on your keyboard, delete. It says also delete all horizontal and vertical grid lines, so you can click on the horizontal, highlight them, and then hit delete on your keyboard, hit the vertical grid lines, and then hit delete again. Okay, and that deletes those. All right, then it says insert major tick marks on the outside of both axes. So let's do that. So you can click on one. Let's do the vertical axis first. Right click. Once it's highlighted, go to Format Axis. Go to Axis Options. Go to Tick Marks. Go to Major Type, and then go on the outside. That adds the tick marks. We can do the same thing to the horizontal. Highlight, right click, Format Axis, Axis Options, go to tick marks, go to Major Type, and then go to outside. That puts tick marks on the horizontal axis. Okay, cool. Next it says include the best fit line. Make it a dotted black line. Again, for more information on the best fit line, please review the PowerPoint. The best fit line essentially is the trend line, okay, of these data here. And so in order to add the best fit line, again, just highlight the graph as I've done. Go to Chart Design, go to Add Chart Element, go to Trend Line, and then go to Linear. Again, in the PowerPoint, it talks about Pearson R correlation coefficient. It signifies, it indicates linear relationships, linear correlations, and so that's why we wanted to put in a linear trend line, a linear best fit line, because that's what we're looking for when we look at Pearson R correlation coefficients. We're looking at linear relationships, so we want to put in a linear best fit line. Okay, cool. So that's how you do it. Okay, very simple, easy. It adds that trend line to the data. And then it says here in parentheses, make it a dotted black line. So let's go ahead and do that. So just click on the line where it's highlighted. Do you see that there? And then once it's highlighted, right click, go to Format Trend Line. Okay, go to, I'm going to move my graph a little bit so you can see. Yeah, highlight it, Format Trend Line, go to Paint Bucket, go to Solid Line, and then change the color to black, which is here. Okay, and you'll notice that that changes it to a black, dotted black line. Okay, so again, the default, it's already dotted. If you want to change, okay, just FYI, you can change that here. Okay, so you can change it to a dotted or a solid line if you wanted to, but again, it asks for a dotted line. Let's use this one here, this round dot, which should be the default. Okay, the default selection here. All right, so now that we've added our best fit line, it's a black dotted line. It says next, use black triangles for markers, size 5, no borders. And so these are the markers here, the data points. All you have to do to change those, notice that they're circles right now. We need to change them to triangles. You can click, and that should highlight all of the data points as I've done here. Go to right click, okay, once all the data points are highlighted, go to right click, go to Format Data Series, go to Paint Bucket, go to Marker, go to Marker Options, go to Built-in, and then change the type to triangles, which is this selection here. Make sure it's size 5, right? Okay, and that's the default. You can change the size here, size 5 default, good. Let's go to Fill next. We need to make them black triangles. Notice how they're blue currently. To make them black, go to Fill, go to Solid Fill, go to Color, and then change it to black. And then finally, the last thing it says no borders. So for border right underneath, go to border and then just go to no line. Okay, no line, that indicates no border. All right, and then that should be it. And then if we click away, yep, sure enough, that looks great. We've got our black triangles, size 5, no borders. Beautiful, okay, for all of our markers or data points. Okay, let's go on. For the horizontal axis, make the minimum bound value 90 and the maximum bound value 160. Okay, so let's go ahead and do that here. Let's change these. I'm going to make my minimum 90 and I'm going to make my maximum 160. Looks like it automatically selected 160 for me. Okay, cool. So minimum bound value 90, maximum bound value 160 for the horizontal axis with major units of 10. Looks like they're already selected, but if we did need to change it, we could change it to 10, just like I've done, and then click away to change it to 10. Okay, again, 10 major units, all that means is that between each value we've got 10 units. Okay, and you can see that here, it goes up by 10 for each one. Okay, so now that we've changed the horizontal axis, let's change the vertical. For the vertical axis, make the minimum bound value 1. Okay, so let's do that. So in order to do that, highlight the axis, right click, format axis. Let's change this to 1.0. Okay, and then it says in the maximum bound value 2.2. Let's take a look and see how that looks on my end. Yeah, that looks okay. That looks all right there. Yeah. Again, remember my data is a little bit different than yours, and so that's why I kind of wanted to take a look and see what it looked like. I could change this if I wanted to. I could change this, for example, to 2.0. All right, if I wanted to. And that actually does look a little bit better. I might do that. But again, remember for your assignment number 4, make sure and follow these instructions exactly, because these instructions are built for your data. Again, remember my data is different than yours, and so my scales, my minimum maximum bounds may be a little bit different as well. And so yeah, I actually kind of like the way it looks there. I might go with this. So I'm going to change my minimum maximum bounds to 1.0 to 2.0. But again, remember for your data, for your assignment 4, make sure and follow these instructions to a T. Make sure and follow them carefully, exactly how I have them here. If you don't, okay, then you'll get points taken off. And then major units of 2.2, excuse me, 0.2. So let's do that. I'm going to do that as well for mine, 0.2 for major units. So now in between each value, right, we've got 0.2. Okay, it goes up by 0.2 in between each one. All right, that looks pretty good right there. So we've changed now the horizontal and vertical axes. We've changed the bounds. That looks good, showcasing our data. Now the next step here, it says add the R and P value. We need to make them size 9 font to the top left corner of the figure. Okay, so somewhere about right in here, top left corner of the figure, that's where we need to add in our R and P value. And this is very common in research when correlation scatter plots are created. Yeah, oftentimes in the scatter plots, especially when we have significant correlations like this one here, okay, where the R value, the correlation is significant, we definitely want to input, okay, the R correlation value and the P value, okay, and then yeah, we already added the trend line. So in order to do that, in order to add the R and P value to the graph, again, highlight the graph as I've done here where the border is selected. Go to Insert, go to Text, go to Text Box. We're going to add a text box. You can do something like this here. And then I'm going to type in, yeah, first R equals, and then I'm going to type in my Pearson R value. Okay, my R value, that's what I'm going to input. So my R value calculated in this problem was negative 0.702. Again, remember also R needs to be italicized, so let's go ahead and do that. Italicize the R. Okay, that looks good. Also, let's include the P value. The P value typically is recorded right underneath the R value, so we can do that as well. So capital P equals our P value. What do we calculate? If we look back up at question number 3, remember we determined what the P value was from the website. The P value is 0.002. Okay, I'm going to make this a little bit bigger, my text box, so you can see both values in their entirety. Again, I'm going to italicize the P value. That's also good practice in research. Most of the time the P value is also italicized just like the R, so make sure and do that for yours as well. I'm also going to zoom in a little bit. So sometimes it's easier, especially when you're inputting things like this. Okay, I'm going to center it here so you can see when you're doing things like this in Excel. Zoom in a little bit, makes it a little bit easier to work with the values, the numbers. And then I'm going to place this in the top left corner, okay, like it says in the instructions. If we go back to question 8, you'll see add the R and P value to the top left corner of the figure. So that's what it means here, top left corner of the graph. That's where we're going to add these two. And then also too, it says size 9 font. So to change the font, highlight the boxes I've done here, go up to the top. You can keep the text the same, Calibra body, that's fine. but then just change the size to size 9. Okay, and then yeah, that shrinks the size of the values a little bit. Okay, that looks good, and then yeah, you can kind of replace if you need to. Okay, in that top left corner, just as I've done here. Okay, that looks pretty good. Alright, now that we've added the R and P value to our graph, it says insert gray break lines for both the horizontal and vertical axes and cover in white the 9 and 90 and the 1 point in 1.0 so that the origins, the starting values on the horizontal and vertical axes are both 0. So yeah, you probably read that and you're like, what the heck, Dr. Palmer, what are you talking about? Okay, yeah, I'm going to show you here, so not to worry. First off, what are these break lines? These break lines, what are those? You've probably seen this maybe in textbooks before. I'm sure you've seen a scatter plot before, like what we're creating here in this graph, where we're looking at correlation between two variables. You've probably seen maybe in a previous textbooks these break lines. What these break lines mean, or what they are, is they're break lines to indicate a space in the data. In just a second, what we're going to do is we're going to make these 0. Okay, we're going to make the origin 0. That's also stated in the instructions. We want the origins to be 0. We're going to make these 0. So imagine just for a second that both of these are 0 right now. So instead of 90, we have a 0. Instead of 1, we have a 0 here. Again, notice the gap. If this was 0 and we go all the way, all of a sudden we go from 0 to 100, and then we start going by 10, 110, 120. Do you see this huge gap that occurs between 0 to 100? Okay, that's a large gap. Okay, that's a large gap, and so in order to indicate that there's a gap there in the data, we use break lines. So that's what the break lines indicate. They indicate a jump, okay, or a gap in the data from one value to another. So oftentimes, yeah, they're right here at the beginning where we have our origin points. And so we're going to do the same thing here. And again, this is all in an attempt to make a high quality graph. It could be very likely that you're going to have to create a correlation graph such as this in the future. Okay, perhaps, you know, if you go into business, let's say, and you're looking at correlation, you're looking at relationship prediction between two variables in business, you might have to create a plot just like we've done here. Okay, and you might have to do this where you add in break lines to make it a high quality graph for a presentation that you're giving, okay, for business. And again, I'm just giving you an example here. Okay, so to do this, to add the break lines, let's do that first. Go to, again, highlight your graph. Okay, make sure and do that first. Highlight your graph so that it's highlighted the border. Go to Insert, go to Illustrations, go to Shapes, and then go to Line. Okay, and then choose Line. And then you can create the line. I always create it kind of like this. It doesn't have to be very big, pretty small. Click and hold, and then you can create a line and then create it at a slant. Okay, did you see how I created it at a slant like this to where it's slanting from left to right? Do it like I just did. Okay, create it just like I did where you create a slant. You can make it maybe a little bit bigger. Yeah, maybe something like that there. Okay, that looks pretty good. And then it says here in the instructions, insert gray break lines. The default a lot of times with these are blue lines, so we need to change that. So you can, after you create your line, you can highlight it, right click, format object, and then go to paint bucket, go to line, go to solid line, and then let's change that to gray. This is a good gray right here. It kind of matches the gray that we have for our axes. So you can click that one there. That works pretty well. And then it changes the line to gray. Now, to create a duplicate break line, and when we create break lines, we want to do this when we want to have two lines that are together. You can just copy and then paste, okay, and make sure and do this while your graph is highlighted like I've done. And then, yeah, paste it here in the graph. And so, yeah, you want these lines to be together, okay, just like I've done here, like I've created. Okay, these parallel lines. And then you can do the same thing. You can create two more, copy, paste, and these break lines are going to go down here for the horizontal axis. Copy, paste, okay, and then you can put them together just like you've done for the other ones. Pretty close together, maybe a little bit further apart. Okay, maybe something like that there. And again, if you need to, you can zoom in. It makes it a little bit easier to work with, especially with these shapes that are really, really small. Okay, so now that we've created our break lines, now we're going to put them into place. And so where are we going to put them? Well, we're going to put one set of break lines here on the vertical axis, and you can put it kind of about halfway, maybe a little bit less than halfway, something about right here. Okay, and you can do it kind of like I've done. That looks pretty good right there. And then you can put the others on the horizontal axis. Okay, maybe something about right there. Okay, and then yeah, about equal space. Okay, something like that there. That looks pretty good. Okay, nice. So again, you can do that when you create your graph. Okay, create those straight lines, change them to gray, and then yeah, you have one set of break lines for the vertical axis, one set of break lines for the horizontal. And again, remember, it's just indicating a gap, okay, a jump in the data from one point to another. And oftentimes it's done right here in the graph where the origins are, okay, to the first data point. Okay, the next step, it says, and I probably should have done this earlier, the next step, it says that we need to cover up, okay, we need to cover in white the 9 and 90 and the point and the 1 point and 1.0 so that the origins, the starting values on the horizontal and vertical axes are both 0. Take a look here and notice before we move on any further, notice that in my vertical axis here, I've got 1, okay, but notice that it's not 1.0. This is actually pretty important, especially for this particular assignment here. It's going to make it a lot easier for us to accomplish this step if we do this. Let's go ahead and add 0.0 to this. Okay, and you'll notice it did the same thing for 2, right? It's just a 2, it's not 2.0. Let's go ahead and do that. So to do that, we can highlight the vertical axis, right-click, Format Axis, go to Axis Options, go all the way down to Number, go to Category, go to Number, and then notice, yeah, Number, Category, Number, and then it has decimal places here. Let's change this to 1, and then you can click away, and then yeah, that should add, right? Yeah, that should add the extra decimal here. So 1 point, instead of just 1, now it's 1.0. Okay, and so yeah, you'll need to do that. What I just showed you here, you'll need to do that for your assignment as well. It also adds that 0.0 up here for the 2. So yeah, so make sure and do that. It's going to make it a lot easier this next step. So yeah, it says next we got to cover in white the 9 and 90. Let's go ahead and do that. Here's a trick. So you might be saying, well, again, what are we trying to do? Well, we're trying to make these origins 0. Again, in a good high quality graph such as this, okay, we want to make the origin 0. And so to do that, you can go, again, highlight your graph, okay, to where it's highlighted around the border. Go to text box. We're going to create a text box. You can create one just like I'm doing here. It doesn't have to be that big, maybe something like that. Okay, highlight the text box just like I've done here. Right click, Format Object. Go to Solid, go to Paint Bucket, go to Solid Fill, go to White. Okay, and that's going to create a white text box. Make sure the line is no line. Make sure there's no line there for the border. We don't want a border around this. And then once we have that, we can click and drag. And then, yeah, you can kind of see what I'm doing here now. And if you need to, again, you can zoom in. Again, it's kind of difficult when you're working with these small shapes. And then you can zoom in, and then you can cover up that 9 and the 90. So now what does it look like? Yeah, now you see what I'm saying right in the instructions. Basically what we're doing is we're having the starting point at 0. Instead of 90, okay, we're going to start the starting point, which should, again, technically all starting points on graphs should be 0. And so again, that's what we're trying to do here. We're trying to make the origin 0. So to do that, we can just do this little cheat here, and we can cover up the first value, okay, in the number. And so for 90 here, we could cover up the 9, and now it looks like it has a 0 as a starting point. Cool. Let's do the same thing for the vertical axis. Let's cover up. And so you can copy and paste, and you can create an identical text box. And then you can drag it down here, and then you can do the same thing. Yeah, you can cover up. Boom, boom. Cool. you can cover up that 1.0. So now it looks like the origin for both the X and the Y axes, for both the horizontal and vertical axes, now the origin is at 0. So that looks really, really good. Okay, yeah, that's a really good high quality graph. I'm going to adjust this just a tad. That looks like a really good high quality graph here now that the origins are both set at 0. And again, you'll do that here, and that's what these instructions are talking about here, what you're going to do for your graph. Okay, so once finished, copy and paste your frequency polygon graph as a picture in the space below. Again, you can copy it directly from Excel, or you can use the snipping tool on your computer. Okay, so I'm going to back up just a little bit here. I'm going to delete this. There we go, something like that. Okay, again, you can kind of zoom in to make it big like this, just like I'm doing. I'll do the snipping tool for this time around. Yeah, I'll go ahead and do that. So again, you can do this, or you can just simply copy, right click, and you can paste your graph and then put it here. Whatever you want to do, whatever is easiest. Again, I talk about, you have both options, and again, give you that option. I've given that before in previous how-to videos, previous assignments. So you can search for a snipping tool, click on it, and then click on this, and then click on new. And let's see, let's move this out of the way. Yeah, let's do this. Click on new. Trying to click on new here. Okay, here we go. Yeah, I was just trying to, I had windows that were popping in my way, so just make sure, get all those windows out of your way before you do the snipping. Okay, so now that we've done that, pull it over there. Yeah, that looks really, really nice. Okay, we've got our graph. Really good looking scatter plot there. Okay, great. And then now that we've done this, create it, just hit copy up here, copy. And then now we're ready to go. You can minimize all these windows, and then now you can insert your graph here under the space provided. Again, you can right click, click on paste options, okay, and then that pastes it there for you as a picture. Okay, great, awesome. Okay, and again, if you need to, you can adjust the size of this. Just make sure it's big, large enough, okay, for me to see. Okay, cool. So last couple questions here. Now, after we've created our nice looking scatter plot, it says for question number 9, determine the equation for the best fit line. So remember, this is the best fit line, right? That's what we created earlier with the trend line. So this is the best fit line here. We need to determine the equation for the best fit line. And again, the reason we're doing this is if you look at the next question, the last question, question number 10, we're going to use this equation that we determined here in question 9. We're going to use this equation to predict. Okay, remember, that's one of the things, one of the primary things that we can get, that we can obtain by examining correlations, relationships, is we can predict, especially when we see a significant relationship like this here, we can predict when we have a significant correlation one variable from another. Okay, and yeah, especially when we have a strong correlation too, like this. Moderate or strong correlations, yeah, they're typically pretty good. Okay, we can use those to help predict one variable from another. Okay, so how do we do this? So how do we determine the equation for the best fit line? Well, if we go back to Excel, let's go back to Excel for a second. What I'm going to do here, I'm going to zoom out just a little bit so you can see. I'm going to click on the graph that I just got through creating. I'm going to click, I'm going to highlight my trend line. I'm going to right click, I'm going to go to Format Trend Line. I'm going to go to Trend Line Options, and then I'm going to go at the bottom and I'm going to click on Display Equation on Chart. This equation right here is the equation for the best fit line. This is the equation that you're going to use. For prediction. And so this is our basically our answer for question number 9. And so yeah, so it's really easy. Yeah, I talk a little bit about this in the PowerPoint. So again, refer to the PowerPoint for more details on this best fit line and the equation. But yeah, Excel, it calculates it. You just saw it. It calculates it automatically. Okay, and so makes it really easy for us. So to calculate the equation for the best fit line, okay, all you have to do is just follow those procedures that I just got through showing you. And so this is the equation here. So let's go ahead and input this equation. Okay, down below for question 9, I've already got the starting point here, y equals, and then yeah, you can just proceed to type in, okay, the equation. So negative 0.0066 x, okay, or a capital X, whichever one you want to is fine, plus 2.3604. Again, when you're typing in this equation here, make sure and type in all of the decimals. Okay, we want to be as specific as possible for this best fit line equation, so make sure and type in all of the values that it has. Okay, don't do any rounding here. Okay, make sure and type in all the values just like I've done here, just like it's presented here in the graph. And so there we go. So now we've got our equation, okay, for our best fit line. And then now let's move on to question 10, last one. Use the equation for the best fit line. So use this equation that we just got through determining here to predict the muscle stiffness value for an individual who has a range of motion of 118 degrees. Okay, so this is where we'll input our answer here. So we're going to use this equation to help predict muscle stiffness for a person who has a range of motion value of 118. Remember, like I talked about earlier in the video, range of motion is pretty easy, okay, especially in comparison to muscle stiffness. Range of motion is pretty easy to measure. It's just a single measurement, and it's that last data point in the angle torque curve. It's really easy to acquire. Stiffness, it takes a little bit more skill. It takes a little bit more time to calculate the slope of the angle torque curve that I showed you earlier. It takes quite a bit of offline analysis to do that. And so yeah, range of motion is quite a bit easier to acquire. And so again, by acquiring a range of motion value, something that's easy, now we can predict the other value, muscle stiffness, that is much harder to acquire. And so again, what I'm trying to indicate here is the benefit. This is the benefit of using prediction, of using correlation. We can predict one variable that's fairly easy to measure, or we can predict one variable that's difficult to measure from another variable that's fairly easy to measure, and this is a perfect example showing that. Okay, so in order to do that, all we have to do is just use our equation to predict the value, and so we can actually do this in Excel. Okay, so I'm going to go down in my Excel sheet, and I'm going to click on an empty cell. You can click on one down below here, that's fine. Okay, just click on an empty cell in your Excel spreadsheet. This is where you're going to type in the equation. And so what we're trying to look for is muscle stiffness. Muscle stiffness, remember, where is it located on our graph? It's located on the y-axis, right? And so y, what does the y in this equation indicate? The y indicates muscle stiffness, okay? So this is the prediction. This is the predicted muscle stiffness value right here. That's it represented by y, okay? Because muscle stiffness is on the y-axis, okay? This is our y variable here. So y, okay, is muscle stiffness equals, okay, and then here we have some constants, all right? This is the slope, right? Again, this is Algebra 101, the equation of the line. This is the slope of the line here, this value. X, what is X going to be? X is going to be our range of motion value. Remember, range of motion, look at our graph. Range of motion is on the x-axis, so it makes sense that range of motion is going to be our x value. Plus, this is a constant right here. This is our y-intercept. And again, this is just Algebra 101, the equation of a line. This is our y-intercept right here. Okay, so yeah, so here's our equation. Let's go ahead, now that we know what everything is, let's go ahead and input it in our cell here in Excel. So you can highlight an empty cell just like I've done, click equals on your keyboard, and then you can proceed to type in the equation. So go negative 0.0066. I'm going to put in, I'm actually going to do this here. I'm going to put this in parentheses. And you might say, well, why are you doing that? Okay, it's not parentheses here. Well, I'm doing that because we want to make sure and do this function first. Notice how these two are together. this value, this 0.0066, this negative 0.0066, it's right next to x. What does that mean? That means that we're going to multiply these two together. Because I want to do this function first before I add this value, okay, which should be the last step, because I want to do this function first, that's why I want to put parentheses in. So just to make sure that Excel does it the way we want it to, that's why I'm putting parentheses here around this first step. So you can do the same thing. So parentheses negative 0.0066 times x. So to do times, on your keyboard, click Shift and hold Shift, and then on your keyboard, press the number 8, and that should provide a multiply sign. This is the multiplied sign, okay, in Excel. All right, so Shift 8, that should provide the multiply sign. And then what's x going to be? Well, x is going to be our range of motion. Remember in the problem, question number 10, it says we're trying to predict muscle stiffness for an individual who has a range of motion of 118. So what's 118? Where's that going to go? That's going to go for x. Okay, that's our x value. We already know what range of motion is. Okay, we already know that the subject has a range of motion of 118. So that's what's going to go here for x. So 118 is what we're going to put here. Then we're going to close parentheses. And then the last step, okay, now it's going to add the y-intercept. We're going to add, so plus, so you can go Shift on your keyboard and then hit the plus sign on your keyboard. That should create a plus sign. 2.3604. And then afterwards, after you've inputted the entire equation, now you can hit enter. And then, yeah, that should provide us with our predicted muscle stiffness value. Again, it says here in the instructions round to the second decimal place, so let's do that. So we have it, look how it's rounded to the fourth decimal place here, 4 decimal places. Let's round it to 2, so let's decrease the decimal to 2 spots. Okay, 1, 2 after the decimal to the right, good. And so that's going to be our answer here. Okay, so our predicted muscle stiffness is 1.58. And again, remember, it's always nice to include the units, Newton meters. Okay, remember muscle stiffness is measured in Newton meters per. And again, you can just take the degree, copy, and paste it. And then you can put it down here. Okay, for degree. Newton meters per degree. Okay, awesome. And so, yeah, so again, what we've done here is we've created a nice looking scatter plot, and then we've used the best fit line in the scatter plot to help us with prediction, okay, to help us predict one value from another. So pretty cool. This is pretty neat. Again, this is one of the benefits of correlation, like I talked about earlier. Think about in real life scenarios. Think about, for example, the weather. Okay, let's take the weather for example. Do meteorologists, do they use prediction? Sure they do, right? Okay, meteorologists predict things all the time. They predict when storms may happen. In hurricane season, for example, they predict where a hurricane may land, okay, where it may hit the shore. How do they predict those things? Well, they use things that we did here today. Okay, they use what we call regression. And again, for more details on regression, take a look at the PowerPoint. It talks about this, but that's basically what we've done. This process of prediction, okay, using correlation, this process of prediction, it's called regression. Okay, and in this case, we're using bivariate regression. Bivariate because bi means two variables. Okay, we have 2 variables here, right? Bivariate regression. Okay, that's what we've done here in this example. That's what we've done in PowerPoint 7 is bivariate regression. But there's other things too called multiple regression. And yeah, that's the premise, okay? That's the premise of making prediction. And so, yeah, when you watch the news at night and you see predictions made by meteorologists on the weather, yeah, basically they're using regression. They're using what we did today, okay, and what we figured out today. They're using that in order to predict storms, okay, when storms may hit, where hurricanes may strike, okay, the United States. They use prediction models. They use regression models, okay, such as we've done here, in order to do that. And so again, what we've done here is very simple. Okay, so keep that in mind. Bivariate regression is very, very simple regression. Okay, the regression that meteorologists use is most likely very complicated. But now you have an idea, right? Now you have an idea after doing this assignment what what is done, okay, what is used in order to predict things on the news, okay, such as weather. Again, that's just one example, right? There's lots of things, okay, that people predict on a daily basis. And again, it's all based upon this premise here. It's based upon regression. It's based upon prediction from correlation. And so again, I hopefully you can hear my enthusiasm here. Again, this is pretty exciting, I think. I think it's pretty cool. And now you've got a knowledge. Now you know how to do it. Okay, now you know how to do it based upon this assignment here. And one more thing that I wanted to touch on is in this graph, again, we showed a negative correlation, a negative relationship. What does this mean? A negative relationship, and again, talk about this in PowerPoint 7, so please refer to that for more details. But a negative correlation basically indicates that individuals that score high on one variable score low on another variable and vice versa. And so again, what does that mean for our example here? Take a look. Subjects over here, like on this side, okay, this side over here on this side of the graph to the right, these are the subjects that scored really high on range of motion. Look at the range of motion values. Okay, it looks like they're all over 150 degrees, really high range of motion. But what about stiffness? Their stiffness values are fairly low. Okay, they're fairly low. They're all, looks like to be all less than about 1.5 and below. As opposed to on the other side of the spectrum, take a look over here. Take a look at these subjects. These subjects over here on the left side, they scored really high on muscle stiffness. They have really high muscle stiffness values. But on the other variable, range of motion, they had very low, right? All their range of motion values, it looks like, are all less than 110 degrees. But their stiffness values are all greater than 1.6 and above. And so that's what a negative relationship is. That's what it indicates, the correlation. It indicates that subjects who score high on one variable score low on the other, and vice versa. And so again, the benefits of correlation. If you provide this information, let's say to a coach, okay, or a physical therapist who's working with these types of athletes, and let's say we identify these athletes maybe here on this side of the spectrum who have really high stiffness values. Because they have high stiffness values, and given the relationship that we found here between stiffness and range of motion, we could put them on a training program. Okay, now that we've uncovered this relationship, this correlation between these two, we could develop a training program that's targeted towards improving range of motion. And by improving range of motion in these subjects, we can perhaps also improve stiffness. We can decrease stiffness. Again, what does this show? This negative correlation, this negative trend line that you see, this best fit line, notice how it slopes from left to right. Okay, it slopes in the downward direction. What does this mean? This just means that as range of motion increases, stiffness decreases. Okay, basically the same thing that I was talking about earlier. And so by developing a training program aimed at increasing range of motion, that can help decrease stiffness in some of these patients and some of these athletes here. Again, given our relationship that we found. And so this is just yet another benefit of correlation. Okay, is that we can, from correlation, we can develop training programs. We can develop interventions now that are targeted towards improving one variable, and by improving one variable, we can perhaps also improve another variable, just like I explained here. By improving range of motion, increasing range of motion, we can decrease stiffness. Okay, and a decrease in stiffness, I talked about earlier, could decrease the risk of injury in our athletes, right? That's a good thing. And so again, what are the implications, right? That's always a good question. What are the implications of our results, of our findings? When we talk about implications for correlation, okay, for relationships, this is yet another implication, okay, another thing that we can gain, another thing that's beneficial to us. Not only is prediction beneficial, but also too, this can help us in the development of training programs aimed at improving the health and performance of our patients, of our athletes, of the individuals that we're working with. Okay, I think that's it. After you've answered all the questions on your assignment 4, Make sure, again, have your name at the top left corner. Have you answered all of the questions for assignment 4? Make sure and save this to your computer. After you've saved your assignment 4 with all of your answers to your computer, then you can go back to Blackboard and you can upload assignment 4 with all of your answers to each question to the Blackboard Dropbox. Okay, I think that's it. Hopefully this video was helpful. I know this video was a little bit longer, okay, than some of our previous videos, but again, if you think about it, there was a couple more questions that we had to answer in this video. Also, too, a lot of the questions that we answered in this video were multi-part questions where we're answering multiple questions within the same question. So again, it does make sense that it did take us a little bit longer in this video. Again, I hope this video is helpful, okay, for you in answering all of your questions for assignment 4. Again, just remember that the data, okay, that you have is different than the data that I had in this how-to video, and so yeah, there's a good chance that a lot of your answers to your questions are going to be different than mine. So again, just keep that in mind. Some of your answers may be the same, okay, some of your answers may be different. All right, so again, yeah, keep that in mind as you're working your assignment 4. Okay, I hope you have a great day. We'll see you next time. Bye-bye.